All right, let's get started. Welcome. This session is about custom layers. I'm Jan Cabon. I'm joined with Jacob. Well, Jacob?
Oh, I like this. It's good. It's good.
Wasilkowski?
Yes, perfect.
Yeah.
Yeah, I'm Esri. I actually work in professional services, and I can be found in our St. Louis office. For those of you who didn't know, we had an office in St. Louis. And also joined with
Thomas.
Yep. Hello, guys. I'm Thomas from the R&D Center in Zurich, and I will cover a little bit of 3D at the end of this session. So, take it on.
Yep. So this is a session about building custom layers. So I will talk about what are layers in 4X, and then we'll go over like how to build a dynamic layer, a tile layer, how to better integrate the layer like develop the layer lifecycle a little bit, and then I'm going to present like some of the new work we are trying to do to enhance the drawing, like more custom drawing, and then Jacob will present a prototype he's been working on, and with that new API, and Thomas will talk to us about 3D. So let's get started. 4X, if you are familiar with the 3X API, in the 3X API, the layer is the component of the API that will fetch the data from a service or hold on graphics, and also be responsible to draw it on the DOM. In 4X, it's different. The layer is only holding on data, and it's responsible of implementing function to fetch the data, fetch images, for example, but it's not responsible of drawing it. What is responsible of drawing it are called layer views, and they are the equivalent of a layer inside the MapView or inside the SceneView. So you may want to create a custom layer in the JavaScript API if, for example, you want to connect to some services that is not supported by the API or not yet supported. You may want to draw some client side. You may work on the data that the layer fetch, like transform it, massage it before drawing it on the screen. Or you may want also to mash up different services together and do a new visualization. So we'll cover like the two type of layers that we support now. Actually, it's three, but the dynamic layer and the tile layer. And then, so this was introduced in 4.4. I think it was Dev Summit release around like April last year. You may find some information in the SDK before going further. If you go into the SDK in the API reference, let me make that bigger. You will find the base classes that I will talk about. You can find them in the API reference. It's called base dynamic layer and base elevation layer and base tile layer. We won't really cover base elevation. We will just like talk a little bit about it towards the end. So you will have explanations about like how to find, how to extend them, and with some example and links to some of the samples in the SDK. All right. So we'll start with a dynamic layer. The dynamic layer, I will show you by the example. Here we have our dynamic layer. It's actually the sample I will talk about. If we look at let's go exploring the sandbox. That's not what I wanted to show, actually. Sorry. So let me make that bigger. The idea of the dynamic layer is that every time, every time I pan, I will release, and we can see that now we have a new image that is exported at the end of the interaction. So if I will filter quickly to only see that service. If I zoom in, boom, at the end we have a new image of the zoom in version. So this is what we call the dynamic expect is like we zoom in, we finish panning, we issue one, we ask for a new version, a new image of the layer. All right. So in 2D, we will ask for one export in general, and then in 3D, it's two exports because we want to have closer to the camera, we want to have more detail, and then further away from the camera, we'll ask for a bigger image, an image that covers more space, but at a higher scale. Okay, so the pros of the dynamic layer is that you can all the processing is done server side and it's dynamic, so you can pass extra parameters to one export of an image. And the problem is that the exact dimension of the image are passed, for example, to the service. And so here in this case we have the width and height of the MapView. And the problem is like every time you will pan, you will get a different URL, so it's not cacheable inside the web, like the browser cache or in the server cache. So it's one of the disadvantages of the dynamic aspect. Okay. So the base class you will want to extend the API with, if I go back to the SDK, is the base dynamic layer. All right. So like I said, you will have all the details, everything that I'm talking about here, it's detailed here. Okay. So how to extend? Once you extend the base dynamic layer class, you can implement two functions: the get image URL. So for that particular bounded box and that particular size, you can override implement that function, return a string, and then we will load that URL, and then it's an image, so we will display it. And then the second hook is a fetch image. So I will show you get image URL example. So from the SDK. So here we have we have the topo base map, and then on top of that I have a WMS service. So in the API we have a WMS layer, so you don't need to do that work, but this is for the example. So let's go over the code. This is the URL to this is the example application. So I'm adding the URL to the service to my course enabled server so that I don't have any issue with proxy and so on. And then I've created a custom WMS layer. So this is not the same of the API, it's just for the example. And I'm defining like multiple properties. So first one is like where is the URL to request for the images, and then the default get map parameters. Okay, and then the second part I create my layer, and then the last step is that I will add the layer to my map. So let's have a look at how a base dynamic layer, you can extend it. So this is made in JavaScript. You can use also TypeScript. We detail in the API guides how to set up with TypeScript and extend our classes. So I create a subclass of my base dynamic layer, and I define the two properties that I want that I will expose as my public API for my layer. And then I override the get image URL, right? So get image URL takes three parameters: the extent, the envelope of what we want to display, and then the width and height in pixels. And then for convenience, I've created two private methods. One is called prepare query that takes the get map parameters that the user set, and then extent, width, and height. And then I join all those parameters into a string, and then I concatenate my get map URL with my query string, and this is what I return. So it's a string to the new image. And so, yeah, that's pretty much everything you have to do here is it's just that. So here, like the prepare query, yeah, takes the get map parameters, the extent, width, and height, and then does some replacement inside for the string and just return the parameters. Okay. Sorry about that. Okay. So that was my example. Then I'm going to talk about custom tile layer. So contrary to the dynamic layer, the tile layer divide the visible space into multiple tiles, so multiple square images that have all the same size, and so we will divide up the space, and for each one of those images, we will ask for the same principle for the URL, and then fetch that as an image and display them. The big advantage over the dynamic layer is that as you pan and as a zoom, we will make more of those requests instead of having to finish the interaction, finishing zooming in or finishing the panning interaction. As you pan, you get more data displayed. And the other advantage is that since we divide the world into a predictable manner, so it's always the same tiles that you will see. Then it's cached. The image that we fetch, they are cached in the browser cache, but also on the CDN or on the server tiers. Finally, the only problem, but this is not really necessarily true, is in general we cache those images, so we can't really refresh easily those images. We have to re-prepare them. Okay, so the different extensibility hooks we have is overriding get tile URL, so it's similar to get image URL, and we can also override the fetch image. So the fetch image is fetching actually taking the URL that is returned by get tile URL and then doing the fetching, like going to use it uses Esri request to fetch the image. What is interesting overriding fetch image is that you can do more processing than just returning a URL. So same, the class to extend is called get tile URL. Sorry, the base tile layer, and same we have all the documentation explaining those different options. So let's go over some examples. So here I'm still in my city in France, where I come from, and as I pan around, we can see that images are pulled from the service. These are imagery from 1951. It's really funny because like none of the place I know existed back then. And let's go over this example. So we have our get tile URL, and very similar to the previous one, it's called tile WMS. I'm still making like WMS request, but in a tile fashion. So and I define pretty much the same options. The big difference here will be that we instead of calling implementing get image URL, we just implement get tile URL. So we have, instead of having a level, an extent and a width and a height, we get the level row column. So if we need an extent, we have implemented some convenient functions like get tile bounds, which gives you an array, which gives you back the extent of the image that you need to fetch. And then same, I build a URL of that, and then I return it, and the rest, the base tile layer does the rest for me. So now I will talk about the fetch tile, where we can actually do more processing. So Stedman here has, it's a studio that makes those very nice base map. This one is called Toner, and it's a black and white base map. And this is a sample of the SDK. What we want to do is that for each one of those tiles, this is not a background. For each one of those tiles, we tint the white part into whatever color we want. So go over. So Fetch style. So this is the app. It's one of the samples also that you will find in the SDK. So I have, I called it tint layer. I pass it a URL template. So I've declared 3 properties: the URL template, the tint I want to apply. We could switch to something like more red. This. Let's try. Right. So it's one of the properties, and then we have a title. So that will be those are the basic properties. Title is one of the basic properties for a layer to be able to display the title in the layer list here. So let's go over the layer quickly. So I define here my properties. All the layers are accessors, so this is how we declare public properties. It's all detailed also in the SDK. So I define a URL template that the user can set and a tint that is of type color. So when I say red, it will automatically convert that to RGBA values for me. I've defined my getTile URL, so level row column. And what I do is that every time it's called, I will just replace from my template curly braces. So those keys in my string, I will replace the Z with the level, X with column, and then Y with row. So if we go back to how it's used, here I define the different pattern that I want to replace. This is just convenience for configurability. And so the fetch style is really what we want to do. So first I use the getTile URL, and then after I use Esri request to query for the image. And then I get back the image. What I will do with that is that I will first draw that image on a canvas and tint that canvas. So I create a canvas 2D, a canvas, and then I get the canvas rendering context 2D. I assign the width and the height of the canvas to the width and the height of my image. So it's going to be 256 by 256, for example. And then if there is a tint, I will draw I will fill that image in red, and then just like use some compositing, draw the image, and instead of returning an image element, I will return a canvas element, because in 2D it doesn't matter if you pass a canvas or an image or even a HTML video element. And that's it. It just draws it on the MapView. So that one's that. Okay, loading and integration. What that means is that when you create a new layer in Forex, the layer is not loaded, meaning that we need to call load on the layer, or the MapView will do that automatically for you. It will. It's a time for the layer to fetch more information. Like, let's say if you are consuming data for a particular service, you may ping the service. Do you really exist, or are you still alive? So that the layer can be considered as loaded. You may as well fetch. What we do during that time is fetch metadata about the service, so we can have the default renderer, for example, in the feature layer, or other information like this. So there is some explanation in the SDK. If you go, of course, if you go to the guides about this pattern, so in the guide, it's called loadable. Here. So more understanding about what is that concept of loadable objects. When they start, they are not loaded. Then we call load on them. They are considered as loading, and then after they are loaded or they are rejected, basically. Okay. So I will illustrate that with an example, which is to reuse the same concept of using the canvas to draw the image, but I will combine two services together. So here is the imagery, the word imagery base map. nothing fancy. And then below it, I have the worldy shade, which are like two services available from the Living Atlas. And what I want to do is to blend the two layers together. So this is my third layer here. So it's I multiply the two images together and I get this visualization. So to contrast with, so this is the regular imagery, and then this is with shaded with the worlded shade. So the principle behind is like I will, every time I will request a tile, I will fetch images, the same image from the world imagery and from the hillshade, and then combine both of them together using canvas, and then return that canvas. So this is the public API that we will expose. We call that a blend layer. It's also a sample available in the SDK. So the blend layer takes as a property called multiply, and I will pass two tile layers to blend together. Can be any of the tile layer, any tile layers, and then a title, and then some other properties there. So if we look at the code of the blend layer, we have defined our multiply property. And then this is the new part. What I want to make sure is that if one of the two layers are not working because the URL points to something that doesn't exist, I will override, I will implement that function called load, and then add a resolving promises. So a resolving promises is a promise that if it rejects, if that promise rejects, the layer will be failed to load. Whereas if all the resolving promises succeeded, then the layer will be considered loaded, and we will start asking for tiles to display or for information. Right, and then so this is the fetch tile function in this case that I implemented. So for each of the layers that are in my multiply, for each of the layers that I want to multiply, I will call fetch tile on the layer. Then, so get all the promises, and when they are all resolved, I will go over all the images and then draw the images one on top of another with the multiply composition. So then I have this blending effect. All right. And then I want to, just like show you some more examples. All those links will be available inside in the proceedings. We have, I made some more examples on GitHub. Yep. It's called bricklayer. So I take the world elevation. It was inspired by this article made by John Nelson about like creating Legoified maps. So it explains the principle about like how to take an image and then pixelate it, and then exaggerating the saturate it a little bit, and then putting a little stud that looks like a Lego brick. So I took this principle and ported that to a custom layer. So made this example. It's using the same Canvas API, and then as you zoom in, it takes the world imagery and do some fancy stuff. Different options. This is the ocean base map, the Nat Geo base map. So it's way more saturated than if it wasn't like pixelated. And then I apply the same principle in one last example. Oops, sorry. It's not what I wanted to do. Oh yeah, here. Is to bin lots of multiple points into different squares. So here we have like 500,000 restaurants that is displayed on the map, but I use the Canvas API to draw them into little squares like this. So they are not real features; they are just drawn as pixels on an image. And this is what you can do with custom layer, for example, like trying to come up with other drawing style. Yes. Okay. So my last point is to talk about like what we have started to work on. The problem of the custom layers is that mostly you have to return images. So everything that I showed you, all the examples are working in both 2D and 3D. So the layer will work the same way. It's pretty nice. But then you can't actually control how fast you want to redraw. You don't have access to the actual canvas that will draw finally the images. So we want to give another hook of extension to create the layer views. So the layer are the access point to the data. The layer views are really what will draw the data on the screen. Yep. So in 3D, there is the concept of external renderers. There is a session tomorrow that if you are interested into extending 3D with custom drawing, you should check out this session by Jesse. It's tomorrow afternoon at 5:30 in Smoke Tree A&E. It's going to be amazing. It created like some very cool stuff for you tomorrow. And for 2D, we want to create custom layer views. So to be able to have more control over the drawing aspects, and we expect that to be released around like in the UC release. So I started prototyping the API. I will show you where we are at the moment. Yep, I forgot to start this demo. Yeah, I mean, it won't really like show you much, but the idea here is that we can see that it looks like an image, but it's actually drawing by the layer view and not by an image. It's the example I gave as a starter for Jacob to start experimenting with that API. So the difference here is I'm creating my custom layer. So my custom layer doesn't do much; it just extends layer. We just have to provide the function, override the function called create layer view that will create the appropriate layer view instance for the map view, the scene view or the map view, right? So in the case of if the view is a map view, then we'll return a custom layer view. And so what the custom layer view is capable of doing, so this will be the name of the base class, base layer view 2D, is that you will be able to start a rendering, export rendering or tile rendering, and you have more control about what's happening. So here, every time we finish to pan and zoom, we will re-render this. We will ask for a new export, and an export is an object with render function. Sorry, it's a lot of information, but it's going to be more interesting from Jacob aspect. You will have to implement a function called render, which is a more low level. So here you will have to actually draw every single pixel on the screen. And with that, I will, Jacob will show us a little bit what he's been working on.
Okay, yeah. I'll switch it over. Okay, so I'm going to have sort of like a case study, if you will. And for a moment, I'm actually going to go back in time a little bit and show you this example canvas, this custom canvas layer in the Esri JavaScript API version 3. And then I'll switch briefly back to extending what Jan was telling us about how to do this in the JS API version 4. So some time ago, a cartographer colleague of mine and I teamed up to make this thing called the Canvas Flow Map layer. And it's actually available on GitHub. You're welcome to go and dig into the source code of how we did this at canvas-flow-map-layer. And again, it's currently out there for JS API 3, and at the moment on a separate branch, which you're also welcome to explore and look at, working off of the API that Janis touched on for version 4. So I'll just jump into a live demo. Again, this is version 3. This is a sandbox demonstration of what this does. And its purpose is to show you the flows between origins and destinations. So if you imagine in this sample, I've just loaded some arbitrary data. It doesn't really matter what it is. And I have an array of graphics that I'm sending into this custom canvas flow map layer. And given this, the lines that you see here from going from the origin of Reykjavik out to many destinations. So you can imagine the flow of goods, the flow of people, even just the flow of ideas. And these lines are not any kind of GIS lines. They're not geographic lines. They're not, if you're thinking of like flight paths, like on a map in an airline, forget about that. They're not geodesic. They're not any kind of routes that were taken in real life. They're actually just simple mathematical curves that we call Bezier curves. So what we do every time you pan and zoom, we grab the GIS spatial coordinates for these points, and we on the fly convert them to simple XY screen coordinates in the browser. And then we hook into a custom canvas element that we have manually added behind the scenes within the Esri map DOM structure, and then we just display these lines in screen space. So for us, that means every time we pan and we zoom, we're redrawing and recalculating the instructions that we sent to the canvas element that we've again jammed in there ourselves. And of course, since we're developers, sometimes we don't know when to stop, so we added more and more features, including these gratuitous animations. So what's cool about this layer too is that it supports different kinds of relationships, of flows from origins to destinations. Conversely, I can have many origins going to one destination, or one-to-one relationships. So you can also, you can get started with this yourself if you follow our README on the GitHub page with your own even CSV files. So part of how this works is that for version 3, it sort of builds upon a graphics layer. And in my case, I wrote it as a new Dojo module using the Dojo declare syntax. And so, again, it extends from the Esri layer's graphics layer. And then from there on, it has quite a few properties and methods to give it life and to give it all the business logic it needs to work, as you saw. So sort of what I hinted at, what's a little bit tricky is we had to construct a browser canvas element on the fly, and then we have to find the exact perfect space in the DOM to put it inside of. And as I sort of mentioned too, every time you pan and zoom, we're converting these spatial coordinates at all these origin and destination points to the XY browser screen coordinates. The other manual thing that this is doing is it's also managing a lot of map event listeners to handle, since we're not, it's not a static, the whole map is not a static thing. You can pan and zoom it as we saw. So I have to check for extent change events. I have to check for when the zoom is beginning. I have to check when the user's panning, and I even have to do some logic when the browser is resizing. And so during those, depending on which one of those events have fired, I'm either like literally moving the canvas around in the browser, or I'm clearing it and telling it to redraw everything from scratch all over again. Or I'm even resizing the canvas itself as the map is resizing if you change your browser size. So then in version 4, and at the moment it's still a work in progress and it's a little bit experimental, the story was quite straightforward. There's a lot less burden on the developer to wire this up. And I'll show you a live demo in a moment. But in this case, we extend from the Esri layer in version 4 and the Esri base layer view 2D. So we create a base layer view 2D, and we use the create subclass method, and that in and of itself has quite a few properties and methods. We also create, we also use a layer.create subclass, which inside of it creates an instance of the custom layer view. And then at the end of all that, we return the layer. So it's a bit of a two-step process, but there's a lot of gains from that make your life a little bit easier if you want to make a 2D non-tiled canvas layer. So we still do a little bit of work to convert spatial coordinates to XY positions, but that's fairly straightforward. What's really nice about this, excuse me, is that we don't have to worry about creating a custom canvas element altogether, and we don't have to try to find out where to put it in the DOM structure at all. And what's really nice too about this, we don't have to wire up and manage and turn on, turn off a lot of different map event listeners. That's taken care of for us. And so again, it's a work in progress, but overall the symbology and the style of this are the same for demonstration purposes. And I'll just actually zoom my browser. So it's the same as what you saw before, version 4. And what's really nice too, that I don't have to worry about, so let me refresh that. I don't have to worry about performing extra mathematical operations myself, which honestly I would be incapable of doing. But I can even rotate this, and it's taking care of that for me. It's really cool. So again, the benefits with when this API is available and stabilized and ready to use, I don't have to worry about, again, creating a custom canvas element, putting it in a very specific place. I don't have to worry about all these map event listeners to help manage the state and reset the view. That's it, more or less. I encourage you to check out the GitHub page if you want to see how the source code is put together for 3 and how it's coming together for 4, and I'll hand it off.
So this API is still like very early work in progress. So if you have like use cases to communicate to us like this week, don't hesitate to hit me up. Yeah, the idea is to facilitate like all the positioning of elements and giving you access to methods to easily convert like special coordinates to screen coordinates that you will redraw. Yep.
All right, so waiting for the image. What was it? 504?
Try 4.
You can. Sorry about that. So, shine my cable. That looks good.
Yep.
All right. All right. Okay, so I would like to present to you the 3D aspect of everything that we saw from our 2 previous presenters. And so first I would like to show 2D and 3D viewing in parallel, then go again just briefly over tiled layers, what Jan already explained, then touch on lurk encoding, which is used in elevation tiles that we serve out from our elevation services. And then go into a practical example. So I'm from Switzerland, and when we do sports in the mountains in the winter, we need to be aware where avalanches might hit us, because it's not so nice to end up in one. And then I would like to walk you through this practical example of really extending that tile layer and doing the sampling and canvas drawing, slope calculation, all that stuff, and finally show you the demo app. All right, so for those of you who haven't seen TypeScript yet, be sure to check it out. This is just a short snippet to show you what TypeScript does for you. My code examples will be in TypeScript, so that's why I wanted to show you this. Basically, it's taking you back to how you learn things should work. So you can define a class, you can define private public properties, and then TypeScript translates that into JavaScript, into this somewhat weird prototype notation that all of us had to get used to when we started with JavaScript. So it's neat. On top of it, it makes sure that when you declare something should be a number, it stays a number throughout your code, and you cannot make it a string, which is good because that's where most of our problems really come from. All right. So the neat thing about the 4X API is that we have these layer containers that Jan introduced, which we call the map. And then we can instantiate a MapView, which is on the left-hand side here, or a SceneView, which is the 3D representation. I linked these 2 views together so that you can see that we're really looking at the same thing. So everything that I will talk about, and most of what was talked about by Jan and Jacob, applies to 3D as well. All right, so these tiled layers that Jan mentioned, they're pretty cool. They span the globe, in different levels of detail. Typically the tiles are 256 by 256, and they have the neat property that the level that we request from a service is the width and height that we will receive in, say, world coordinates is inversely proportional to the power of 2 times, or the power of 2, the level, power of 2 to the level, excuse me. And the level can go down to 15, which is roughly 1 mile for a tile, sometimes even all the way down to 22, which would be 10 yards. And to show you how it looks like, I hacked into our API, and you can see how the tiles look like for the view that we had before. So we have a very large tile here in the background, and smaller tiles where the camera was at. And this really makes for a neat, seamless integration into whatever view you request from the API. All right, so what I will do in this custom tile layer example here is I will do a hybrid sort of approach. So I will do a tile layer, but I will actually sample from an elevation service. So I will not sample from an image service. And then I will calculate a slope. And in Avalanche theory, and as I mentioned, we have a lot of that in Switzerland, there's like this classification that we use. So below 30 degrees is typically fine. 30 to 35, you need to be already aware what you're doing. Then 35 to 40 is pretty dangerous already. 44 to 45 is, I would never go there. And above 45 is you basically need a rope and mountaineering equipment to really do it. And then we want to display that data on top of the map. So just a brief notice on the lurk encoding that we get from the elevation service that we're sampling. So it's open source, and it allows for lossless compression or user-defined loss during the compression. Typically, as I mentioned, the elevation data is encoded in lurk, and there's a publicly available JavaScript implementation for you to look at. All right, this is a repetition of what Jan showed us, but bear in mind that this is TypeScript. So this is how it looks like in TypeScript. We extend the base tile layer and call it custom tile layer here. Then these are the 2 public properties or methods that we need to implement to be a tile layer in the view of the API. And then there's a bunch of properties that I require for this specific example to work. So should we shade the hills, and then which direction should we shade? You will see that later in detail. All right, so then one thing I do in my fetch tile implementation is that I actually upsample. By upsampling, I mean I actually draw the data that I'm retrieving from a tile that's a couple of levels up and not from what I'm looking at. This allows me to have different levels that I use from the elevation service as from the image service. This is neat because it increases performance and reduces load on the network. We can cache tiles more efficiently like this. Plus, it gives me a coarser representation, which is actually advantageous, as you might see later, for the visualization that I'm trying to do here. So my upsampling level, if the level that I'm requesting is above 5, my upsampling level is just 2 up from the level that I'm looking at right now. So from the level I should request to have optimal resolution, pixel resolution. Then I define my upsampling rate. And then the row and column I need to fetch from the service is actually different for each level. So here, this notation, as you might remember, is just a shift to the right. It's basically a division by 2 to the power of upsampling rate. And the same for the column. And then the thing I do next is I actually request the tile at that upsampled level, upsampled row, upsampled column, and hand that over to Esri request, which will handle all the necessary procedures to retrieve data from the network. All right, this is also basically just reiterating what Jan already showed us, the canvas drawing example. So it's pretty neat. I mean, in 3D, we use the 3D canvas. So when we draw in 3D, instead of writing 2D here, we write 3D, and then we get the full interface to WebGL. But we don't need to do that because we're really just assembling a 2D image here at this point. So we're good with the 2D context. Note that here the width that I will have in my image that I'm composing is actually divided by that upsampling factor, because I'm not retrieving data at that resolution but at a lower resolution. Alright, then I'll create that image data container that I will be able to fill, and what I do here in this simple example, I will just randomly select the channel, and then if that channel is red or green or blue, I will set that pixel to 255 and the alpha channel to 32, and that's it. Here's how it looks like if I execute that, and I get a somewhat weird looking, almost like old school TV problem view of the Earth. Alright, then now we actually get into a little more details of what I'm trying to do. So to sample from that upsample tile. Why isn't this coming? That's better. Excuse me. So I'm sampling from that upsample tile. The data that comes back is this response data, and I need to decode it with this lurk decoder that I showed you before. That's available on GitHub. And once I have that lurk data, I need to find my coordinate in that lurk sample. Since it's from a level higher, I can't sample the full lurk data, but I need to find my like shift from the left and shift from the top, which is this upsampling factor. So say I'm at column 12 now, but say, okay, so I'm looking at column 10, but I'm upsampling from a higher level, so I need to shift myself to the right in that data to find that column 12 that I should be looking at. Same applies for row, and then I define a very simple sampling kernel, which just samples pixels to the left, to the right, to the bottom, and to the top. And what I do here, I need to know the length of the pixel. This is somewhat of an approximation, but works good enough. So Earth circumference divided by the pixels that I have in that lurk tile, and then divided by the level that I'm actually looking at here, will give me the length per pixel. And then I walk the image, calculate XY coordinates, and start my sampling routine here by setting max and min to minus and plus infinity. And then I retrieve a sample from the lurk data, and as you might expect, I drive my max and min to finally calculate a slope angle, which is a little bit of trigonometry, the arcus tangents of the max minus min. I sampled across 3 pixels, so I need to divide by 3, and also need to divide by the length of the pixel, and then conversion from radians to degrees. Nothing spectacular here. And what I'm doing in this visualization here is I multiply the slope that I calculated by 10 to drive the red channel. Green and blue are 0 and alpha 128. And this is how the slope looks like. But this is not really useful yet to do like avalanche analysis or the danger of avalanches. So what I need to do there is this classification, and this is nothing too spectacular either, but what I showed you before, if the slope is above 45 or above 40, above 35, above 30, I get these different colors. And then alpha is set such that if we have a slope below 30, we don't draw anything, so we draw alpha 0 and basically a black pixel, and otherwise 128, so halfway transparent. And this is how it looks like on this particular section of the Earth I'm looking at. And since I already calculated the slope, and since some of the base maps have kind of I would say, suboptimal representation of hill shading. I can make advantage of this algorithm. All I need to add is I need to sample the center pixel. And once I have the center pixel, I need to see if one of the samples, the left, top, right, or below, is actually lower than the center pixel. If that's the case, and then I'm looking at a slope, which is inclined into some direction, either northeast, south, or west. And this one here will tell me that if that sampling kernel X component is positive, so I'm looking to the east, then I want to shade. You could have shades to the north, to the south, to the west. This one will make it appear in the east. And here again, if I'm shading, I have a alpha of 32, otherwise it's transparent. So this previously white map now suddenly becomes a bit more understandable what the mountains could look like. And bear in mind, there's no elevation loaded, so it's everything that you're seeing here is really the relief calculation from this custom tile layer. All right, and then to put everything together, this is really all the JavaScript you need to make that map happen, to make that avalanche tile layer happen, give it the elevation layer as URL, create that map, add that layer, create the scene view, and yeah, you're all set. So let me reload this page so that you can see how it performs. So this, we're looking at the Matterhorn, which is probably the most famous mountain in Switzerland. And you see there's plenty of above 45 degrees, even plenty of above 40. So it doesn't look like a place you want to go if there's plenty of snow. But maybe you could sneak through here and then maybe take this route and maybe be very careful here or be very careful here and then take that ridge all the way to here and you could survive. So, I mean, this is what mountain guides use in Switzerland to actually determine if something is feasible or not. And I think it's pretty cool that with a couple of lines we can make that happen dynamically and in this sense accessible for everyone on this planet if the elevation service covers that area, and it does cover a lot of area. It's just out of curiosity, see, I mean, I don't think that there's ever snow here, but maybe. So how does it look like here? Alright, there's plenty of dangerous slopes here if there would be snow. I guess the general concept is applicable to other type of dangers in the mountains. So if you have a lot of rain, say over the last 2 or 3 days, you wouldn't be surprised if rocks start behaving like snow and dirt starts behaving like snow. So, yep, that's pretty much it. One last thing. So we didn't really touch on extending the elevation layer. Here is a simple example that just exaggerates elevation. You will recognize the similarities. So the exaggeration factor here is 100. We're using the same elevation service as we saw in the Avalanche example. And then there's this fetch tile method that we need to override. So we fetch the elevation from our own internal elevation service. Once we get a response at a certain level, row and column, we find out what the exaggeration should be. We iterate through all the data points and multiply them, and that's what we return. And we can feed that in to the map here into the ground property, which is something that holds layers property, which is an array of elevation layers. We give it this new exaggerated elevation layer, and you see that all things that we draw on the map that actually make use of this ground layer are exaggerated by 100. And so this is just something that I wrote down. So we could sample more points or sample across tile boundaries. This is currently not implemented. We could detect the highest available level that the service offers us. And then if you would really were to be serious about this app, then you would probably also want to bring in weather data to know like what were the conditions in the last 2 or 3 days. And what we do in Switzerland, and that's pretty neat. So there's guys like cutting off a block of snow and like really separating it from the rest of the slope. And then they jump on top of it and they see if one of the layers breaks off. And if it does, then they try to find out like, yeah, how deep is that layer that's still stable? And then they publish that data in chart form that's not human readable. But anyway, it adds to our vast information pool. All right, and I guess that's it. Thanks for your attendance, and we're happy to take your questions now.